Hello, everyone, and thank you for attending Lab Manager's Green Labs Digital Summit. My name is Mary Beth DiDonna, and I'll be moderating this discussion. As more companies move toward a more sustainable future, labs are following suit by planning facilities that are more flexible to deal with changes in research and science. It's important to remember that a more sustainable lab can't be developed overnight. Lab managers should take a look at the small changes they can make now to save time and money down the road. The Green Labs Digital Summit is a series of informative webinars from experts who will share their experiences in the sustainable lab and will offer advice to help you green your own lab through lower energy consumption, less landfill waste, and more sustainable work processes. Welcome to this session, Recirculating Chillers Designed for Today's Green Labs. Today's chillers are vastly different from their predecessors, offering precise temperature control for laboratory and analytical equipment while delivering energy, size, and noise reduction and environmental impact savings. This versatility allows lab managers to reduce upfront equipment costs and long-term maintenance costs, while increasing lab space and being environmentally compliant. This webinar will discuss the latest in recirculating chiller technology and how modern laboratories can achieve environmental compliance, reduce operating costs, and increase equipment uptime. Our speaker has also invited you to participate in a poll, which you should see on your screen now, and this will help him learn more about our audience and offer additional insight during his presentation. Lab Manager likes our webinars to be very interactive, so we encourage you to send us your questions at any point during today's webinar. Our speaker will address these questions during the Q&A session following his presentation. To ask your question or leave a comment, simply type your query into the Q&A box, which is located on the right-hand side of your screen. We'll try to address as many questions as possible during our time together, but if we run out of time, I will forward any unanswered questions to today's speaker, and he can respond to you directly if possible. Additional resources and handouts for today's presentation are located on the right-hand side of your screen in the Handouts section. And the Handouts section also includes more information about our Lab Manager Academy management courses. I would like to remind you that the recording of this webinar will be available for free on-demand viewing after the conclusion of this event. And I would like to thank our sponsors whose support allows Lab Manager to keep these webinars free of charge for our readers. So with that, I'd like to introduce our presenter for this webinar. Greg Ducharme is the Product Director for the Liquid Cooling Systems product area at Laird Thermal Systems. Prior to joining LTS, Greg has been involved in sales, engineering, and project management of thermal solutions for the medical, analytical, and industrial market segments. In these roles, he has gained valuable business operations and technical experience in working with demanding global companies. For over 20 years, he's been closely involved in delivering engineered and configured-to-order products for customer applications. Greg holds a master's degree in business administration from the University of New Hampshire and a Bachelor of Science degree from the Worcester Polytechnic Institute in Massachusetts. Greg, thanks for joining us today.
Thank you. All right, so get right into this. I'm going to be talking a little bit about chillers today, how they're used in labs. I'm going to cover a couple of different topics. Want to give you a little bit of a background on who Laird Thermal Systems is, what we do. Talk a little bit about refrigerants used today in the industry. Talk about some of the products that Laird offers that can be used in laboratory applications, as well as their use of, most of which use refrigerants. Talk a little bit about sizing of products, and then kind of wrap up with some information that's available to customers like yourselves for understanding what's available in the market in terms of products. So, the next slide. So, just to give you a little bit of a background about who Laird is. We're a manufacturer of cooling components and systems that are used in a number of different applications, primarily medical, analytical, and industrial. We also do a little bit of work in transportation and some work in telecom as well. We have a very diverse product portfolio. We manufacture our own thermoelectric modules that can be used for cooling fractions of a watt. We also implement these into assemblies where they can be used to cool hundreds of watts, both direct contact cooling as well as air-to-air cooling. And then we also make systems that can cool up to kilowatts, some of which go into tens of kilowatts worth of cooling capacities. We do we solve a number of complex issues for our customers. So a lot of the products that we make are being integrated into their system. So we, in addition to the thermal requirements that we're working with, we also have a number of size constraints. Customers are always looking for smaller solutions to be able to cool larger and larger heat loads. We have a global engineering team that works closely with our customers in order to develop innovative solutions. We're trying to work in the same time zone as these customers in order to accelerate their time to market in the ease of interaction with our customer base. And as I mentioned, we're always trying to maximize the performance of our product. I'll talk a little bit about some of the challenges associated with some of today's technologies from the industry that are kind of presenting further challenges in order to realize those performance requirements that our customers are interested in. So I want to take a quick look. I'm going to take a break after this the introduction here to see what's been put on the poll to make sure I'm going to be addressing some of these topics. It looks like right now, if I looked at the top three, energy conservation is a big interest to the audience today, followed by ease of use and noise levels. So and precise temperature control. So those are kind of the top three. They're all great topics, all of which are going to be discussed within this presentation. So hopefully I answer some of the questions you may have about those, and if not, feel free to use the Q&A area where you can ask follow-up questions on the topics. So within the laboratory applications, there's a number of different uses for cooling equipment. Some of these applications are cooling electronics. So when we think of electronics that are used in maybe a high-power microscope, electron microscopes, mass spectrometry, also in some chromatography type applications, thermal management is of increasing importance there in order to improve the performance of the instrument. We also do a lot of work with incubation and cell growth, so precise temperature control is really important here as well in order to really create the environment for most efficient growth in those types of applications. And then we also do work with maintaining temperatures for reactions, and a good example here is where we provide liquid cooling for the condensing and rotary evaporators. So this is another important application that's within the laboratory space. So a lot of these laboratory environments are in chemistry, biology, some industrial, oil and gas, and a number of research and food science types applications. So very diverse customer base that's using this type of equipment. So when we look at some of the requirements associated with laboratory certifications, there's a lot of work today within making laboratories green. So LEED, being LEED certified, is one of the foremost means of proving that your building or your laboratory is green. So this is a leadership in energy and environmental design. A lot of places use this to show that they're being environmentally responsible, but there are also places where there are tax breaks and whatnot to be able to be LEED certified. RoHS certification is another important certification for a lot of components. This has its kind of roots a couple decades ago in more of the electronics industry, but a lot of this has come into a wide range of components. When we look at plumbing components, for example, a lot of bronze fittings back in the day had lead content that is no longer allowable today. So RoHS has evolved over the years. There's a RoHS 2 now, and there's also kind of another similar type of standard, REACH, which is really, this is putting a limitation on what kind of metals can be used. So a lot of limitations on mercury, lead, some of the chromates and whatnot. UL lab standards, this is another important one. So this is UL is the kind of the North American equivalent of CSA or some of the IEC standards. One of the parts of getting a product either UL listed or UL registered is that it's going to be a safe product that can be used by laboratory technicians. So making sure that they can't freely access moving parts. So when we think of heat transfer, we think of fans. So making sure that they're protected from that, as well as live components, electrically live components. So we want to make sure all those parts are only accessible by using a tool. So we don't want to have it happen by accident. And so then the second part of having a part UL registered or recognized is electromagnetic compatibility. So we want to make sure that these products can interact within the lab with other technologies that are there from an emissions and immunity standpoint. We want to make sure that we're not causing harm to other products, and at the same time making sure that our systems can work too. And finally, the last one, when we think of chillers, the use of refrigerants is a big topic these days. Today, it has a lot more to do with global warming potential. We'll talk more about some of the history of refrigerants and how they've evolved. But this is really changing what's being used, especially in the laboratory environment, because these tend to be more of the lower capacity systems. And so this is a good place where the use of alternative refrigerants can be put to use. So looking at some of the refrigerants, and how they've evolved over the years, we can break this down into 3 generations, so to speak, of refrigerant evolvement. And the first was in the mid 19th century with the introduction of refrigeration. At the time, this was focused on using a lot of natural and hydrocarbon refrigerants. This was kind of a whatever worked type of mentality. This had a lot of safety problems associated with it. So a lot of the refrigerants were toxic, they were flammable. And so as refrigeration technology evolved over the years, it came into kind of what we call the second generation, which had to do with safety and stability of the products. And so this was a big move in the mid 20th century to CFCs, or chlorofluorocarbons. And so by the name chloro that's in the CFCs, this is got high chlorine content. And chlorine is the part of the refrigerant that interacts with oxygen to deplete the ozone layer. So these refrigerants were high in ozone depletion, and they also had strong global warming potentials. So as much as they were safe equipment, it was really poor for the environment. And you can see some of the milestones that started taking place in the late 20th century that brought about some of the change associated with the third generation. So this was more aimed at reducing impacts on the ozone. And so this was a switch to hydrochlorofluorocarbons and hydrofluorocarbons. These had significantly lower amounts of chlorine, and some of the refrigerants which had absolutely none, that had no impact on the ozone depleting potential. But at the same time, these still had a high GWP, or higher GWP than what we're really trying to go today. And this is what is happening in the fourth generation, or what we call the global warming sensitive generation. So these you can see we've kind of come back to where we started nearly 200 years ago in using some of the natural and hydrocarbon refrigerants. And so these have no chlorine, so there's zero ozone depleting potential, and they also have very, very low, some have zero global warming potential. And so we can look a little bit more specifically at what some of these are. You can see on the upper right-hand side here, ASHRAE has put together a classification, if you will, for the types of refrigerants in terms of their flammability and toxicity. The first character, the letter in the code, indicates the toxicity, so whether it's an A or a B toxicity class. And then the higher the number, the higher the flammability in the second character. So as we go from an A1 up to an A3. And you can see that there's, when we look a little bit closer at the table on the left, there's certainly a balance between the flammability and the global warming potential of the refrigerants. As the global warming potential goes down, there tends to be a higher flammability rating. And so when we look at that table, in the upper left-hand corner, the first, the CFC and HCFCs, these are the refrigerants associated with generation 2 that I shown on the previous slide. And you can see the ozone depletion potential is high, is up around 1, but some of the GWPs are extremely high, R12 being the highest at over 10,000. And you can see from an ASHRAE rating standpoint, these are all safe refrigerants, but very poor for the environment. As we moved into the third generation of refrigerants and HFCs, you can see there's a reduction in the ODP and a slight reduction on some of the GWPs. As we get into where we are today with alternative and natural refrigerants, you can see that there's still a zero ODP, a greatly reduced GWP, and a increased flammability and toxicity of the refrigerants as we go to some of these propanes and isobutanes that are being used as for cooling. And so this presents some issues from a technical design standpoint, from a safety, where we're trying to design systems that can withstand very high pressures in order to make sure that they're going to be safe for operation in the industry. And so furthermore, there's, as part of the phase down of some of these refrigerants, there's a concern over price. And so a lot of these refrigerants that are being phased out, there are fewer companies that are manufacturing them, and so they become harder to get, and the demand is going up for less supply, and as a result, there's an increase in price. And so in addition to the environmental positives of using some of these refrigerants, there's also a cost positive of being able to use refrigerants that are becoming more readily available. So when we look at some of the standards that kind of govern the use of refrigerants in products, there's a couple of different categories. One being whether or not this is a household type of appliance or some similar type of household appliance, and that all falls under this European norm, or EN, or IEC 60335. And so this governs a couple of different types of products, whether they be refrigerating products, displays, appliances, heat pumps. And then outside of that, there's within EN 61010, this is the laboratory safety standard for equipment used in the labs. And so this is more of an industrial type of application that has its own requirements around use of refrigerants in labs. All of these norms have their own specific standards, but then they also rely upon EN 378, which is what I show here in the bigger orange area that kind of has a fallback of use of refrigerants in general. And so then I show outside of this, in this black area, there's another very specific standard around that comes from the IATA, which is the International Air Transportation Association. And so they have, for obvious reasons, some requirements in terms of how much of this refrigerant can be used, especially if it's a flammable refrigerant. So they put limitations upon how much can go into a single system that they're going to be transporting around the world. And we'll talk a little bit more about that. Just to give you a visual of some of the products, this is the same type of image that I showed on the previous slide, just with actual products. So you can see 60335 is the household or similar type of equipment that is presenting standards for refrigeration use, heat pumps, freezer displays, and then in the lower right here, I show some more industrial equipment or laboratory equipment under which the cooling systems tend to apply. That then has requirements that kind of fall back on this EN 378 refrigeration standard. So when companies are designing equipment that uses refrigerants, there's a couple of important questions that we need to ask ourselves before we start delivering these products to our customers. And this really has to do with the flammable refrigerants. And the first is whether or not this is going to be a product that's going to be air freighted around the world. As global as the industry is today, most products are sent by air, whether it's sent initially or by customers at the end. We really need to consider that. We can send it by ground to our customers, but how is our customer going to get it to their end customer? And so this all needs to be well thought out. If the product is going to go by air freight, the IATA has a requirement that the refrigerant charge in the system be 100 grams or less. And when we think about that, the amount of refrigerant put into a system directly impacts how much the cooling capacity of the system can be. So 100 grams is not a lot of refrigerant. A lot of chillers today that use some of the standard industry refrigerants will have charges of half a kilogram, which is 5 times what we're talking about here. And those are only cooling about 5 kilowatts. So with 100 grams, there's a real need to have some design expertise in order to maximize the cooling performance of the system while still keeping that refrigerant charge down. And so we'll talk a little bit more about some of the technologies that we use in our systems in order to improve that. The second question we need to look at is whether or not this is an industrial application. If it's not an industrial application, the 60335-2 applies to this, and they have their own limitations. So these are the household or similar type of applications. Depending upon the classification of the flammability and toxicity of the refrigerant, it's either a half kilogram charge or 1.2 kilogram, and a pressure test requirement of 3.5 times the operating pressure. If it is an industrial application, then we need to look at what the refrigerant charge of the product is. And so if it's greater than 150 grams, it applies to the 61010-2 standard. That's if it's less than that. If it's greater than that, then it's the EN 378. And so these also have their limitations as to how much the charge can be, but all of them generally, you can see here, are driving towards a pressure test or pressure rating of 3 times typical operating. So a lot of this expertise has been pushed down into the manufacturers, where we need to come up with these safe operating systems that can work with these refrigerants that normally haven't been safe over the years. So when we look at some of the products that Laird supplies into the lab space, we have 2 types of cooling systems that we provide. One we call liquid heat exchangers. So these are ambient systems that are cooling a fluid directly, either with air or another liquid. So think of your car engine is an air-cooled or an ambient-cooled system. We also make systems that will use a facility water loop that maybe isn't at the precise temperature or at the precise flow rate that a customer needs. And we can work with those irregularities of temperature and flow to provide the customer with a real precise coolant loop. We also offer products that can cool below ambient temperatures, and so we do this 2 ways. We do this with thermoelectric technology, and we also do this with refrigeration systems. So these are vapor compression systems. And so these really, the 2 products here, the common thread amongst most of the products we make here, are that they have a pump circulating fluid out to the customer's application. One is typically at above ambient temperatures for bulk heat removal, and this is the liquid heat exchangers. The second is the liquid recirculating chillers, that is more of a precise temperature control heat removal product. That it's really the precision of the system is actually enabling the end instrument to perform at a higher level. So again, think of electron microscopes that need a high level of stability in order to really create an image that is magnified many thousand times what the real part is. So there's a number of benefits that these liquid cooling systems provide within the analytical space. One is high heat pumping capacity. So when we think about the actual part that's being cooled, we're passing a liquid through some type of channel, whether it be a cold plated or a simple tube that's immersed in liquid. This has got a much higher heat capacity than that of air. So when we think of a thin heat sink mounted on a component that's blowing air over this, there's also an ability to remove heat from very high heat flux density applications. So electronics are a big one here. This has to do with the high thermal conductivity of the liquids, the heat capacity, as well as the amount of mass flow that we can send through one of these components when you think of it relative to air. Heat routing is very simple with liquid cooling systems. We can put fluid through a 1/2 inch or a 12 millimeter hose that can go to and from the application and remove kilowatts worth of heat. And when you think of that in comparison to an air duct would be many times that, and you'd also have all this air that's kind of howling through the duct. So it's very simple to get the heat from the application out into, say, an equipment room where the cooling system could be installed. These systems are also, because they have higher cooling capacities, they have the ability to cool down rapidly. So a 5 kilowatt system that maybe is on startup that needs to get to temperature, get to the set point, can do it in a matter of minutes. given the flow rate that's running through the system. These systems also, because of the high heat routing, they can be lower noise, have a lower noise impact to the lab, either by being installed remotely, but at the same time, a lot of users like to have these close by. So a lot of the chiller manufacturers these days have taken this into account, especially in analytical applications, where we're trying to lower the noise of the actual system, whether it be the pump, the compressor, or the condensing fan. And I'll talk a little bit more about that in a minute. So when we look at the system that Laird has recently launched, this is what we call the NextStream platform. In the course of 2021, we've released a product that we call our performance chiller. And so this is a chiller that uses premium components that's available in the market at a mid-tier price. So we use a number of well-known brands here. Whether it be an EBM fan or a spec pump or a Danfoss or Tecumseh. These are very well-known, proven suppliers in the industry that are known for high performance, low noise, that are really desirable within these types of applications. The systems are also designed to cool well below ambient temperatures. Laird has developed the control technology in these systems ourselves. So with our thermal expertise on both thermoelectrics as well as liquid cooling systems, we put that to use here in order to really optimize how the thermal performance of the system is achieved, rather than using an off-the-shelf controller that can be applied to many different types of applications. We've really taken user-friendliness into account here. The system itself the interaction with the system is through a touchscreen LCD display. So we recognize that users of the equipment in laboratories are not spending a lot of time with the chillers, and so we need to make that time as efficient as possible. And so with the touchscreen LCD, we're able to communicate directly with the user. So if there's an alarm on the system, we can display specifically with text what that alarm is, rather than displaying an alarm code that then needs to be looked up in the manual and we need to figure out what's going on. We can very quickly look at the system, understand how it's operating, and take action if necessary. The system also has very low noise. There's a couple of reasons for this. One of them is the actual fan that's been used in the system. So I had mentioned earlier that some of the technological advances in heat exchangers has come a long way. So a couple of decades ago, maybe even just 10 years ago, the majority of the condensing units that were used in these systems of condenser heat exchangers were we call a tube fin variety. So very low performance, maybe 70% efficient. The technology that's commonly used today and what's been employed here is a microchannel heat exchanger. So very efficient heat exchange takes place here, probably upwards of 90%. And so what does that mean? That means that the heat exchanger can be smaller, and it also means that less airflow is necessary in order to achieve that amount of performance. And so with less airflow, we get less noise. The refrigerant that's used here also, gone over this a little bit, but the one that we use in this product is called R513A. This is kind of a half step between what's commonly used in the industry today and getting to those alternative near zero GWP refrigerants that are becoming more of the norm. So this refrigerant has anywhere from about half to 1/8 of the GWP that's commonly used in the industry today. So it's about half of R134A, and then if we look at some of the other ones like R404A, it's about 1/8 of that. So another feature that we've implemented into this product design is variable speed. So we did this on the compressor and the condenser fan. We did this specifically on those two motors because that's where the performance of the system varies the most. So the customer always has a need for constant flow rate. So the putting design and cost into variable speed on the pump motor wasn't as important to us as it is on the compressor. These systems often will be in a standby state where they're cooling a very low load for extended periods of time and then called into action where they need to cool at 90%. So with the variable speed compressor and fan, we're able, in that standby mode, we're able to really slow down those motors, and that does a couple of things. It reduces the amount of noise within the system. within the installation site, and it also reduces the energy consumption. And so this is important to any lab space that's looking to, that's really has a priority on being green. Let's see, slide. So looking closer at some of the specifications of this product. So there's 4 products in this performance series chiller product range. The first is the 400 watt unit. This has most recently been launched. This uses thermoelectric technology as the cooling. There is 3 other larger refrigeration-based products. One is 1600 watt, another at 2800 watt, and another at 4900 watts. These are all nominal cooling capacities, often in the industry specified at 20 degrees C ambient and 20 degrees C set point. You can see the set point range here ranges anywhere from a little bit below 0, a little bit below freezing, upwards to 40 degrees Celsius. The temperature stability is a fraction of a degree. So on the thermoelectric side, often with lower heat inputs, lower cooling capacities, it's easier to achieve higher temperature precision. So this is at 0.05. And then the refrigeration-based systems can achieve a 1/10 of a degree temperature stability. The thermoelectric product, the NRC 400, is available in what we call a universal voltage. So this all of the system components run on DC voltage, so they can handle anywhere from 100 to 230 volts input and be able to run the system. The larger systems are more, instead of calling them universal, we call them global. So they're available in the 200 to 240 volt, 50, 60 hertz globally. The smaller unit's also available as a North American model in the 100 to 120 volt, as well as in Japan. So looking closer at the thermoelectric product, again, this is part of the performance series. So we're using premium components. This as a cooling engine is what we call, instead of the refrigeration system, uses Laird thermoelectric modules. So these are modules that have passed rigorous reliability testing, as well as being used in a number of harsh environments in both the telecommunications and the transportation industries. The temperature stability, as I mentioned, is 0.05 degrees C. This comes from decades of Laird engineers working on controlling thermoelectric modules. So we have a vast amount of experience in terms of not only making the modules, but also understanding how to control them. The system itself has about 30% higher cooling capacity than some of our previous products. A lot of this has to do with improvements in the thermoelectric module technology, as well as some of the heat exchange technologies that are used. This has solid state technology for its cooling in the thermal engine. So this is a semiconductor component with no moving parts. So this obviously has a number of advantages, not only from a noise standpoint, but also from a reliability component. In terms of user friendliness, this uses the same platform user interface that's used on all the refrigeration products as well. So again, touchscreen LCD for ease of access, very intuitive in terms of being able to use. And from a environmental standpoint, obviously with no refrigerant, this has 0 global warming potential. And if we take a quick look at what the insides of one of these thermoelectric chillers, so within the dotted line here, we have, similar to the refrigeration systems that in any of the liquid cooling systems that we supply, they have a tank and a pump that's used to circulate the fluid. But the cooling is actually taking place within a thermoelectric or a Peltier device. So what we have here is a liquid cooled block that's mounted to the cold side of the thermoelectric, and the thermoelectric acts as a heat pump to pump the energy out of the liquid block through the Peltier and then into a finned heatsink on an air side of the Peltier. And so this is the general concept under which they work. These systems also, because they're lower cooling capacities, they also tend to have lower flow rates, and so this is really conducive to mag drive pumps, and so magnetically coupled pump motors are even more reliable since there's no mechanical seal that can potentially leak over time. So thermoelectric products are great for low cooling capacities where where the benefits of the coefficient of performance of the systems is not as great when you get into the larger cooling capacities. So a thermoelectric product that has a coefficient of performance of 1 that's cooling 400 watts, whether or not that energy consumption is 400 watts or 1 kilowatt is not as significant. But when we get into the larger systems, it does become more important. And that's where the real benefit takes over of a refrigeration product. Somewhere around 400 or 500 watts is kind of the crossover point. And when we get up into those larger capacities, refrigeration systems have a coefficient of performance around 3. And so what that means is in order to cool 3 kilowatts of energy from or remove it from an application, we only need 1 kilowatt of energy. And so the real important part here of what we've introduced with the variable speed compressor and fan in this is that we're able to sustain that high level COP even at low loads. So if we competing products that use a single speed motor or on both the compressor and the fan, when they get into a standby mode, they're still consuming the same amount of energy or a very similar amount. But we're able to slow those motors down and consume less energy, which we feel is very important to the use of the product. So when we look at the product itself, so I'd already mentioned the R513A refrigerant, very low GWP, and the variable speed motors that are used. And so this has obviously lower noise and there's some energy savings as well. But another thing that we need to keep in mind is the impact on the installed site. So with us consuming less energy, it also means we're rejecting less heat into the environment. And so this has a lower impact on the HVA system of which the chiller is installed. When we look at the inside of the system, there are typically 3 heat exchangers that are used in order to reject heat from an application, the first being in the customer's instrument. And so in this case, we show a laser and a power supply that's being cooled. And so that's where the first heat exchanger is, that's taking heat away from electronics. As the liquid comes back into the chiller, represented by the dashed line, the first heat exchanger within the chiller is what we call the evaporator. And it's called that because it's actually vaporizing the refrigerant on the refrigerant side of the heat exchanger. So the liquid goes through the evaporator, it's cooled, stored in a tank before it goes back out to a pump and back out to the application. On the refrigerant side, the evaporator is the means of exchanging heat from the coolant and the refrigerant. The compressor forces the refrigerant through another heat exchanger, which is called the condenser. And this is where the heat's rejected into the local environment. There are some systems that have liquid-cooled condensers, but I would say the majority of them out in the field are air-cooled. So when we look at what this product offers in terms of reliability and maintenance, I mentioned the proven components and suppliers, technologies within the industry that we use. We also use, of those suppliers, some of their technologies that are very reliable. So the pump, for example, we use a pump in the system that's called a turbine pump. So it's a regenerative turbine, which has near zero wear parts in the pump itself. So this gives us about 4 times the expected life of some of the competing technologies in the market. We also have a lot of instrumentation put into the system so that we can monitor the operation and the health of the system over its lifetime. There's about 25 alarms that can indicate either something is starting to go wrong, that we need attention in order to prevent some unwanted downtime. We also have options available to the system, one of which is a hot swappable filter. So a lot of these install sites have maintenance that is required to, or maintenance personnel that's required to do any work on these systems. And so changing of a water filter could result in some downtime, whereas all this system has to be done is put into bypass and the filter can be replaced. Another important part of this system is that the hydraulic system has what's called a pressure cap on the reservoir. And so we call this is a semi-closed system. A lot of the chillers out there in the market today have vented systems, and these are really easy to install and get up and running. But the downside is there's a lot of evaporative losses, and there's a lot of interaction with the environment around in which it's installed. And so this can be dust, it can be biogrowth. And so what our system is it's a pressure cap. So again, with the automobile analogy, the radiator on the front of an automobile has a pressure cap, and it seals off the system from the external environment unless high pressures are achieved. And so that's what we have. Under normal operating pressures, this system is closed off from the environment all the time. There's no biogrowth, there's no evaporative losses, and this really provides a distinct advantage for our users. When you think of how an automobile cooling system, the maintenance that's required on that, it might be 100,000 miles, which depending upon how many miles you drive, it could be upwards of 8 years. So we really anticipate that this is a very low maintenance design that can provide some true benefits to our customers. So real quickly, I just want to talk a little bit about what it takes to size a chiller. The whole goal is to take heat away from the application. And so in order to do this, there's a heat exchanger that in the example I had shown of the laser that's been designed under specific conditions in order to function properly. And so with a certain heat input, the heat exchanger will need a certain flow and temperature in order to transfer that heat. And so that's exactly what we need to know in order to size our chiller. We need to know how much heat's being put into the fluid. We need to know what type of fluid it is, because there's different fluid properties, thermal properties that impact the performance of the system. We need to know at what temperature that fluid needs to be and how much of it they need. What is the flow rate? And so oftentimes this information is provided by the manufacturers of the equipment, but sometimes it's not. And so we can get by with what is a pretty simple experiment in order to find out some of this information. And we can use tap water in order to determine what these requirements are. So with the instrument installed and operational, we can run tap water through the system. So in this experiment, we know our fluid is water. And while the water is running, we can fill a bucket. Knowing what the volume is of the bucket, we can time how long it takes to fill that bucket. And this gives us a volume per time, which can be our flow rate. And then we can measure the temperature of the liquid going into the system, and then the temperature coming out of the system while it's while it's being used in full heat removal capacity. And so with that, we get our set point. That's the temperature inlet. And then if we can take the temperature rise, so temperature rise, knowing what our mass flow is through the system and what type of fluid that is, we can use a pretty simple calculation here in order to determine what the heat load is. Albeit this is a little bit, I'd say, crude and simple. It gives us a good starting point, and with some margin on top of these calculations, we can size a product that can meet our cooling needs. And so if we take that information and take a look at what a typical cooling performance curve of a chiller looks like, we can begin the process of selecting that chiller. So this chart here shows the performance of Laird's NRC 1200 chiller. You can see on the y-axis there's cooling capacity in terms of watts. That is a function of the fluid temperature set point. So you can see as the fluid temperature goes down, the set point is reduced, so is the cooling capacity. We also have a kind of 3 pairs of cooling performance curves here. The top 2 are both water and a glycol mix at 20 degrees C ambient. The middle 2 is at 30 degrees C ambient, and the bottom 2 are at 40 degrees C ambient. So you can also see here that as the temperature of the install or the ambient condition increases, so does the cooling capacity decrease. So there's a couple of things these are a couple of things we just need to keep in mind when sizing the product. And you can see that with the pairs of fluids, so the top curve is being all water, and then the one right below that is a 60-40% water ethylene glycol mix. There's a slight decrease in performance, maybe in the 5 to 10% range. It's certainly not as significant as the other 2, the set point and the ambient. So if we take a quick example here of a chiller that that's needed in order to provide 6 liters per minute of water at 20 degrees C to cool a laser, that's generating 2,000 watts. If we were to look at the NRC 1200 performance curve in the upper left-hand corner of this slide, you can see we start with the cooling capacity on the y-axis and go across until we meet what the performance set point is, the fluid temperature set point. And you can see here that that performance point is above the capacity of the 1200. So that doesn't meet the performance. So we need to go to the next size larger model. In Laird's case, that's the NRC 2400. And when we do the same thing here, we see that we're below the performance curves of both of the of all the conditions, whether it be a different type of fluid or an ambient condition. So that gives us the correct size refrigeration system. And the second part is being able to find a pump that meets that performance. And so in this case, we needed 6 liters per minute. If we go to our performance curve of the pump for the NRC 2400, you can see that at 6 liters per minute, the system is capable of delivering about 3.5 bar of pressure. So that's a little bit over 50 psi. And so that's at 50 hertz. If we were to look at the 60 hertz curve, which is the higher, the green one, the higher of the two, you can see the performance is increased due to the higher motor speed. So there's a couple of things that we need to keep in mind when we size pumps within chillers. The pressure loss of the system, so this is the inlet pressure minus the outlet pressure. So this is what's required in order to move the flow through the instrument or through the application. The pressure drop within a system, it's proportional to the flow. So in this case, on the chart example on the right, you can see the blue line. As the flow increases, so does the pressure. It's exponential with a square relationship. But the thing to notice here is that pump curve, just like a fan curve, it's inversely related to the flow, the pressure and flow are. And so as the required flow goes up, so does the pressure decrease. So we need to keep that in mind, that this is kind of a double-sided sword here, that applications that need more and more flow, there's two challenges that presents. More flow means more pressure drop in the system, and at the same time, a given pump is capable of less pressure at a higher flow. So it's a delicate balancing act. And so there's other things that we need to keep in mind about pressure. Elevation change is another one. Now, in pumping systems, when we're pumping up to an application and then the flow is coming back to the cooling system, yes, it takes additional pressure to pump that fluid up, but we get that additional pressure we kind of get back for free when gravity does its work against the fluid to pull it back down to the system. But the one thing we need to keep in mind is that we need to be able to deliver that flow the first time. So if there's a system install that's pumping up a number of stories, say 30, 40 feet, we need to make sure that pump can create that additional head, that initial head, in order to deliver the flow up the first time. Hose dimensions and fittings is another important one. We need to keep in mind the size of the hose. So I would say on the low end, 3/8 of an inch or maybe 8 millimeters of hose. Probably like to see a little bit larger than that, maybe 1/2 inch, 12 millimeter. The smaller the hose, the higher the pressure drop, as well as any additional fittings or connections that are put into the fluid lines. So whether these be flow meters or valves, they all impact the pressure drop of the application. Water filters are another one that requires special attention. So water filters, yes, have a pressure drop that they introduce into the system, but it's a variable pressure drop. So a filter has a given pressure drop when it starts out clean, and as it's used over time and gets dirty, that pressure drop will continue to rise. And so we need to keep an eye on those filters and make sure that they're clean. In applications that require less flow than what the pump can deliver, we have there's a number of ways that you can get to that operating point. We offer an optional kit that it consists of a bypass valve assembly as well as a flow meter, so you're able to really dial in exactly what that flow rate is. And so this is usually sufficient for most applications, because all of these they tend to have a single operating point that just is set up at the time of install. So in terms of support for our users, our customers, the Laird website has information on the NextStream series page, where you can see descriptions about the products themselves, how they function. We have interactive data sheets where you can select specific use cases to understand how the product works. We have a technical library that's filled with application notes and catalogs, presentations, some videos about some of our technologies and our products. We also have a chiller support page where manuals and training videos can be viewed as well for support. when you go to some of our the landing page on the product, you can see here we have the applications for some typical applications that you can read about in terms of how the application, not only how the product works, but how the application works to give a better understanding of the technology. Descriptions of our accessories that are available, as well as a kind of a high-level table of the products that are available and standard data sheets. You can also check on availability and pricing with our distribution partners. So this is all real-time inventory. And then if there's additional questions, you can always reach out to the product support or request a quote for the product all through our website. We also have a tool on our website that we call the Thermal Wizard. This is a web-based sizing tool that helps select the best product for your application. You can input temperatures, flow rates, or either directly as numbers or use the sliding bars to help select your requirements. The output of this is a suggested solution for your application from a thermal management standpoint. You can then take this information is then stored in the event that there's future questions or discussion points that you want to have with some of our product support people. They can look at what was done to size the product and to make sure that it's the correct product for your application. So when we look in summary, there's a number of applications that require cooling within laboratories. A lot of the instruments that are used today are becoming more and more powerful and becoming smaller. So what does this mean? This means higher heat densities, more cooling required, and as a result, liquid cooling has become widely accepted within laboratories. Chillers are an efficient solution for this. They can provide much more precise temperature and flow rate over a tap water or a central facility system. And the systems are also much more mobile. So when they can be used in one lab and then need to be removed to the next, it's very simple. It doesn't require any plumbing in terms of bringing those cooling lines over to the new application. All industries in general are moving towards greener solutions. For chillers, this has a lot to do with the refrigerants, and it also has to do with lower energy consumption. And that's really what Laird has done with the NextStream product, has targeted some of these important environmental topics. And we're going to continue to do that in the future with some future products that we're currently developing today and that will be released in the years to come. So I want to thank you for joining on this, and I think we'll hand it back over. And if there are any questions that have come in during this presentation, I'd be more than happy to answer them.
Okay, great. Thanks very much, Greg. As Greg said, at this time, we're going to move into our Q&A session with the audience. But first, we'd like to invite you to participate in a special poll, which you should see now. This is where you can submit your own tip for achieving a green lab, and you will have a chance to win a gift card courtesy of Lab Manager. So please input your answers into that poll if you would like, and then we will carry on with the Q&A. For those of you who may have joined us late in the Q&A, I'd like to remind you that you can submit your questions or comments for Greg by typing them into the question box, which is located on the right-hand side of your screen. So Greg, the first question we have from the audience is, and if you look at the Q&A box on your screen, you should be able to see them all if you could scroll down. What is the temperature range of thermoelectric chillers like the benchtop model?
Okay, so there's, when we talk temperature range, I'm going to go back to there's two things that we need to keep in mind. One is the temperature. I assume this is probably the set point range. So set point range of the product is -5 degrees C to 40 degrees C. Now, we can follow up either with what a performance curve looks like for a thermoelectric chiller. These are based on temperature differentials. So it's not as, it depends on where you're coming from. If you're a refrigeration person, it seems more complicated. If you're a thermoelectric, it seems easier. So it's a temperature differential. So if we're running the system at 0 degrees C differential, meaning the set point of the fluid is the same as the ambient temperature, it's capable of 400 watts. When we want to cool below that ambient temperature, that cooling capacity decreases. So it's related to the refrigerant, but it has a different, definitely more directly impacted by the ambient temperature. So from an operating range standpoint, this is, in terms of the ambient conditions, I believe it's more a typical 10 to 40 degrees C ambient, but that ambient temperature is going to directly impact the set point that you're capable of achieving. So I hope I answered that question accurately. If not, please reach out to us. We can follow up. But I think looking at a performance curve of a thermoelectric product will help understand that better too.
Okay, great. Thank you. We have another question here, and it says, when does it make sense to consider refrigeration versus thermoelectric systems?
Yeah, so this is a good question. And I tried to cover that with the COP topic. So thermoelectric components as part of a system are good for, I'd say, typically up to a couple hundred watts, probably 500 watts might be the high end. And the reason being is the energy consumption required to cool heat loads larger than that. So when we think of a coefficient of performance of 1, in order to cool those 500 watts, we're talking about an energy input of 500 watts. And so that any savings by using a refrigeration system that might be 3 to 1. So in order to cool 500 watts, we're putting in, say, 200 watts. That differential is minimal. But when we get into larger systems, that energy consumption becomes a little bit more significant, as well as the required airflow and to cool the thermoelectrics. At the same time, smaller systems, the thermoelectric is more conducive because of the initial cost of a refrigeration system for cooling small loads. Although the technology does exist, some of these miniature components, miniature compressors are very expensive. And so when we think about replacing a full refrigeration system with a thermoelectric assembly, it becomes quite economical. But when we get into larger systems, it's really difficult to do with thermoelectrics, especially a liquid-to-air thermoelectric engine. We can use thermoelectrics for cooling higher heat loads that are liquid-cooled. So when this has got liquid flowing through the hot side as well as the cold side, these become a little bit more efficient, require obviously no airflow. But to answer the question directly, I would say 500 watts is probably a good cutoff point, a good transition from thermoelectric into refrigeration products.
All right, great, thanks. We have time for a few more questions from the audience. So the next one here says, how are pumps sized for these systems?
Sure. So pumps tend, in terms of the pump performance, it tends to be proportional to the heat load that's being cooled or the amount of energy being transferred. So that may not make sense on the surface, but what tends to happen in applications is that equipment manufacturers are trying to maintain a certain temperature rise across their product. So with higher heat inputs, in order to keep that temperature rise constant, they increase the flow rate. So in the example I had given, we'll go to this slide just to provide the visual. In this equation that's shown here in bullet 4 on the bottom, heat load is proportional to the mass flow rate times the temperature rise. So if heat load's going up and we're trying to maintain the temperature rise constant, then we need to increase the flow rate. And so typically, using imperial units, well, kind of a mix, I guess, for every kilowatt of heat, it tends to be about a gallon a minute, so 4 liters per minute or so. And so as those heat loads get up higher, a 4 kilowatt system would use around 4 gallons a minute or 15 liters per minute or somewhere in that range. So, but we need to keep in mind the pressures associated with those higher flows, as I discussed also, right? So we get into higher flow rates, and this requires larger tubes and heat exchangers that have lower pressure drops in them in order to accommodate those higher flows.
Okay, great, thanks. We have another question here that says, how easy is it to manage the exhaust heat?
Yeah, so this can be done a couple of ways. The the first is, so the system can always be installed uh, in the location of use of the end instrument, and we just need to keep in mind the amount of heat that's being rejected into the environment. One, for a comfort level of the user, we want to make sure we're not pouring too much heat onto them, but then also we need to make sure that the air conditioning or the HVAC system can handle this additional load. So in addition to taking all the heat out of the application and rejecting that into the air, the compressor in the system is also cooled by the refrigerant. And so this heat is being rejected as well. Tends to be about a 30% increase above the total heat load of the application. So in the case of a 3 kilowatt cooling application, you're rejecting a total of 4 kilowatts into the environment. And so we need to, one, make sure that the HVAC system can handle that. If there's an issue with this being a lot of heat, put either locally to the technician or to the instrument that's being cooled. I talked a little bit about heat routing. This can be easily installed into an equipment room that has its own dedicated HVAC and cooling to take on that heat, and we can use those small hoses that I had mentioned to run back and forth, maybe with some insulation around them to prevent additional losses. But it's generally pretty straightforward. We're not talking about tens of kilowatts of heat. When we started getting into those higher cooling capacity systems, these become outdoor installations, either maybe in a shed outside or on a rooftop, where they can handle the elements, and then also those tens of kilowatts of heat can be rejected directly into the outside environment.
Great, thank you. I think we have
Yeah,
time for two more questions.
perfect.
Are there limits to the ambient temperatures the devices can handle before impacting performance?
Yeah, certainly. So refrigeration systems, you can see that on the performance curves of the systems that you see a degradation of its capability to provide cooling as the ambient temperature increases. And so this is a direct result of the condenser that's cooling the refrigerant. So as that temperature rises, it's decreasing the efficiency of that heat exchanger, and it's impacting the amount of cooling that can be provided to the evaporator and then cooling the hydraulic loop. So that's one thing that needs to be considered. Certainly the operation of the refrigeration system, but there's always a concern in terms of electronics operating at high ambient temperatures, motors. The rule of thumb is every 10 degrees increase in temperature, I think, is a reduction of half of the life of an electrical component or a motor. So this is always something to keep in mind. These systems can operate upwards of 40 to 50 degrees C, so it really depends upon the specific application, but I would always recommend individuals to reach out to us directly if they have a need that's higher than what's stated on the data sheets.
Great, thank you. We have time
Mhm.
for one last question. If one of the standard models doesn't quite fit an application, can you offer any advice on product selection?
Yeah, perfect. So yeah, just as I had said with the ambient conditions, I think this is always, manufacturers, Laird included, we're always trying to provide standard products that can serve a wide, um, purpose to our customer base. But at the end of the day, there are going to be some application specific requirements that we can always entertain. Obviously, there's got to be some. It needs to make economical sense for both parties in terms of the time for us to develop the product, as well as what we're willing to pay for the product. So yeah, we try to use standard products as much as possible. This gives us economies of scale that we can then pass on to the users in terms of an attractive price and a product that's also proven in terms of the components that we use. We like to take parts that have been used years over years and continue to use them, knowing that we have some confidence in their ability to perform in the field.
All right, wonderful. Thanks so much. So
Yeah.
this brings us to the end of this webinar, and I would just like to remind all of you that this webinar will be available for free on demand shortly following this live presentation. So you can watch your emails for a message from Lab Manager, or you can visit the Green Labs Summit website, which is at the bottom of your screen right now, and we will post the message there once they are available. So on behalf of Lab Manager, I'd like to thank Greg Ducharme for all of the hard work he put into his presentation, and I'd like to thank all of you for taking time out of your busy schedules to join us today. Once again, thank you to our sponsors, Agilent Elemental Machines, Equipnet, LabConco, Laird Thermal Systems, Peak Scientific, and Watt IQ, whose support allows Lab Manager to keep these webinars free of charge for our readers. This concludes Lab Manager's Green Labs Digital Summit. All 7 of the presentations from this digital event will be available for free on demand. So again, watch your emails or visit summit.labmanager.com/greenlabs. For more information on all of our upcoming or on-demand webinars, or to learn more about the latest tools and technologies for the laboratory, please visit our website at labmanager.com. We hope you can join us again. Thank you to all of you for being part of our Green Labs Digital Summit, and we hope you have a great day.